Welcome to the next lecture in the series on condensed matter theory. In this video I want to talk about phase transitions with an unconventional order parameter, namely the irreducible representation, which can be used as an order parameter. If we think of phase transitions, then we can use Landau's theory. And within Landau's theory we look at the free energy, because we know from statistical physics that it's the free energy that is minimum at finite temperature and not the internal energy. And the free energy is a function of temperature and theta, the order parameter. And we can make a Taylor series expansion, alpha 0 plus alpha 2 theta square, alpha 4 theta to the fourth, alpha 6 theta to the sixth, etc. And what we have seen before is that we can distinguish between first order phase transitions, where the order parameter is discontinuous and jumps at the critical temperature, and you can have overheating up to T0 or undercooling up to T1. Or we can have second order phase transitions where the order parameter itself is continuous at Tc, but its derivative is not, as a function of temperature. Now if you look at the free energy as a function of your order parameter, then at high temperatures for first order phase transitions, this has its minimum at theta equal to 0 for T larger than T0. Then at intermediate temperatures we have 3 minima when T is larger than T1 but smaller than T0. So T is between T0 and T1. And then at low temperatures we have again only 2 minima, a maximum at theta 0 when T is smaller than T1. Such that you have a phase transition from theta is 0 at high temperatures to a finite value of theta at low temperatures, and that's a 0 and not theta. And for a second order phase transition we only have 2 cases. You either have at high temperatures a minimum at theta equal to 0, or at low temperatures you have 2 minima at finite theta, T smaller than Tc. Now the order parameter in Landau's original paper is related to a reduction of symmetry. And for example, if you go from a cubic lattice and have a phase transition to an orthorhombic lattice, then we can define theta as the angle of 2 of the crystal axes, and in the cubic lattice theta is 0, in the orthorhombic lattice theta has a finite value, and that is exactly what you have at your phase transition. So your high temperature phase is the symmetric cubic one, and your low temperature phase is then the distorted orthorhombic one. And of course, for different types of lattices you can define your order parameter in different ways. Now not all phase transitions have a reduction of symmetry. It's a very important class of phase transitions. But for example, if you have a transition between a gas and the liquid phase, then we can take the density as the order parameter, where the gas and the liquid phase have different densities. Now, what I want to talk about in this video is a case where we take for the order parameter the phase, and I put it in brackets, the ground state wave function gets under a symmetry operation of the point group of the Hamiltonian, or the space group under a symmetry operation of the space group of your Hamiltonian. So we have the psi1 is e to the I theta 1, psi1, and then we have a phase transition to another state where the psi2 is e to the I theta 2, psi2. For example, you can have a phase transition between an even and an odd wave function. T would then be the inversion operator where r goes to minus r, and in one phase you have a plus sign, in the other phase you acquire a minus sign. So phase is put here in brackets because, well, if it's a single fold degenerate state or a one-dimensional irreducible representation, then indeed this is just a phase. To be more general, we have to say that we look at the character table, or the character of the wave function changes. So for non-degenerate states, you look at the phase that you acquire, or for single-fold, single-dimensional representations, you look at the phase you require under your symmetry operations. For multi-dimensional states, degenerate states, you look at the trace of the matrix that tells you what the transformation is. You look at for all symmetry operations, and that is your character. A generalization of even and odd states that we have. And in order to then make the statement a bit more exact, we look at the irreducible representation and we say we have a phase transition because the irreducible representation of your ground state changes. So in the standard case, it is the space group of the Hamiltonian that changes, but we can also have a case where the space group of your Hamiltonian stays the same, but the irreducible representation of the ground state wave function changes in that system. Now let's have a look at an example how this can be possible. And for that we can think of a phase transition between an even and an odd state. So I have an even state, psi gerade, and an odd state, psi ungerade. Both are eigenstates of your Hamiltonian, and I now want that at some temperature one is the ground state and at some other temperature the other is the ground state. So my Hamiltonian has to be temperature dependent, but that within the same space group. So we do not change the space group of your Hamiltonian, but we can change some parameters inside the Hamiltonian. So I have a temperature dependent Hamiltonian, and both the gerade as well as the odd ungerade wave functions are eigenstates of that Hamiltonian. And let's take a different color for the two states. We can then make an energy level diagram where we look at the energy as a function of temperature. And let's say we have at some temperature a phase transition. Now below that phase transition temperature, I'm just going to take a temperature independent Hamiltonian. This is just an artificial example I'm not looking at a particular material. And above the transition temperature, we can have an energy dependence of the even and odd state. And this would definitely give you a phase transition and a discontinuity in the, or non-analyticity in the free energy, and truly be a phase transition. Instead of looking as the Hamiltonian as a function of temperature, I actually do not know of a material example where this truly happens. I know of material examples where this happens combined with a reduction of symmetry of your Hamiltonian, and it might well be that this is the driving force and the space group is just following, but where you have truly an example of a system like this, I am not aware of a material. But we can think of phase transitions not only as a function of temperature, but for example as function of pressure, or as function of a magnetic field. Then we have our critical pressure or critical field, and we have an energy dependence of the even, the odd, and the even state. And well, of course, it not necessarily has to be even and odd. If I have one state with a magnetic moment and one state without a magnetic moment, you can easily see that this would happen in a magnetic field. One is paramagnetic, the other ferromagnetic, and you would get behavior like this inside the magnetic field, giving rise to a phase transition at t equals 0. And this is what is known as a quantum phase transition. So if you think, for example, of an iron 2+ atom or an even iron in the metallic phase, you have a local magnetic moment. If you put pressure on that system, at some point that local magnetic moment collapses, and then you have a phase transition between a magnetic and a non-magnetic state as a function of pressure. So that changes the irreducible representation of your wave function, but not necessarily also the symmetry of your Hamiltonian. So you can stay in the same space group and just have a different irreducible representation in your system. You can make also molecular magnets, where as a function of magnetic field you will make a transition from a non-magnetic local configuration where the spins are antiparallel to a magnetic local configuration where all spins become parallel. And again, you can have, but you must not necessarily have, a reduction of the symmetry of your molecule, but you do change the local irreducible representation. Now let's have a look at a tight binding example where we have an even to an odd phase transition. A tight binding model with an even to odd transition. And this is an example that we will come back to in later lectures as well, as we can not only use it for phase transitions where we change the irreducible representation, but we can also use it for phase transitions where we change the topology of the wave function. So in my example, I will make a one-dimensional chain. I will assume a basis of s and pz orbitals. I will assume that I have nearest neighbor hopping. So I have my lattice sites and a hopping between them. It's an infinite lattice. And I will assume that I have 2 electrons per side. So I have 2 electrons, I have 2 orbitals with spin, that's 4 orbitals, so we will be half filled. If the bands don't cross, I will have one band that is filled and one band that is empty, such that you're insulating. Now if we look at our hopping, then we have the interaction between s electrons, which we will label from s to s, making a sigma bond, ss sigma, and our matrix element ss sigma is smaller than 0, which is important to know if you have electron or hole-like bands in your system. So this will give you electron-like bands. Then we have the odd orbital, our pz orbital. The interaction between them we will call pp sigma, hopping from a p to a p orbital, making a sigma bond. For the s hopping you have a plus lobe to a plus lobe. Here we have a plus lobe interacting with a minus lobe. So pp sigma is of opposite sign and therefore larger than 0. Then we have the interaction between the s and the p orbital. And our sp from s to p hopping integral is hopping from plus to minus. So also the sp sigma matrix element is larger than 0. You have to be careful because, well, for the s hopping it doesn't matter if you hop to the right or to the left. The same is true for the p hopping, you always have a minus and a plus lobe. If we however have an even and an odd orbital in our hopping and we would hop in the other direction, then you see that here a plus lobe is pointing towards a plus lobe. So the hopping from an s to a pz in the negative direction is the matrix element minus sp sigma. That becomes important if you look at the Hamiltonian. And let's make the s orbital magenta and the p orbital blue. So we have our creation of the s and the pz orbital. Then we have a 2 by 2 matrix for our Hamiltonian, epsilon s plus 2, ss sigma, cosine ka, epsilon p plus 2, pp sigma, cosine ka. And then on the off diagonal we have a sine-like hopping, because hopping to the right and to the left, e to the plus ikx, e to the minus ikx, have opposite sign, giving you a sine instead of a cosine wave function. And then again we have our annihilation operators for the pz and the s orbital. So that results in our Hamiltonian. We can now have a look at the k-dependent eigenstates of our Hamiltonian. And now as a function of the interaction, as a function of epsilon s minus epsilon p, we see that either the s orbital is above or the s orbital is below the pz orbital. Whereas in these plots we assumed that sp sigma is 0, such that our Hamiltonian is diagonal on the basis of s and pz orbitals, and there is no mixing between them. So for our case where sp sigma is equal to 0, we can take epsilon p smaller than epsilon s plus the bandwidth of the s orbital plus the bandwidth of the p orbital. And when this is true, then the pz orbital is occupied, because the pz orbital is then below the s orbital. We can have a look at the case where epsilon s is smaller than epsilon p plus 2 ss sigma minus 2 pp sigma. In that case the s orbital is doubly occupied. In both two cases we are an insulator. And then we can have a look at the case where epsilon s minus epsilon p S smaller than 2 SS sigma plus 2 pp sigma. And in this case we have a metal. So we see here for the middle two cases your bands overlap and you're two metallic. For the outer cases one of the two bands is below or above the other. Then when we introduce an interaction between them, we find an insulator. Because an hybridization gap opens between the two bands, there is one case that we have to take as an exception. Because our hopping matrix elements scale with sign Ka, we know that there is no mixing between them at K is 0 or K is pi over A. So exactly at the point where the difference between the on-site energy is the bandwidth of your s orbital plus the bandwidth of the p orbital, your bands touch and either touch at gamma or at x. So we have 2 points where your system is metallic and otherwise the system is insulating when you have this interaction between your bands. Now the question we want to answer is if these bands are even or odd. So we have our lowest band completely occupied and we have 4 different cases here, or 2 different cases, S band completely below, P band completely below, or a mixture of the 2 bands. Now, is the wave function where all these states are occupied even or odd? So in order to address this question, we can have a look at our wave function. And our state is given by the product where we sum over all k vectors and band indices, and we want to include those where the energy of the state is smaller than the Fermi energy, and in that case we create that state out of the vacuum. And what we want to determine is if we act with the symmetry operator where r is replaced by minus r on that wave function, do we then get a plus or a minus times that wave function? We know that you're in an eigenstate of the Hamiltonian. The Hamiltonian has inversion symmetry, so it must also be an eigenstate of the inversion operator. And the eigenstates of the inversion symmetry operator are either even or odd. So we have either a plus 1 as eigenvalue or a minus 1 as eigenvalue. So let's start for the case where SP sigma is 0, and I want to only look at the insulating states. So we assume that we have 2 cases, or we have restricted ourselves to 2 cases. We either have psi s, where we have a product of all wave functions, where we create an S Bloch wave function or an S Bloch state at a certain k vector, or we have the pz many electron state, where for each k value we create the pz orbital at all k values. And we want to know, is this state even or odd, and is this state even or odd? And be careful if you think you can easily see the answer, because this is an S state when an S orbital is even, and this is a P state and the P orbital is odd. We have to do a bit more work than just look at the single particle wave functions in there. So let's first see how the Bloch states transform under inversion symmetry. So I'm looking at R 2 minus R of A dagger, Ks out of the vacuum, and this is T, and now let's write out the Bloch state as a sum over local Wannier functions. which is my square root 1 over v, whereby v is in units of unit cell volume. So some authors like to write n there, the sum over the number of unit cells, e to the I k dot r, a dagger rs out of the vacuum. And now we have to look what your inversion operator is doing, and the inversion operator acts on small r, so it's not going to do with my face, but we have to see how the small r entered here in your local Wannier function. So let's see what t a dagger rs is. And this is equivalent, now not written as a state, but as a wave function, an S wave function centered around the point r minus capital R. Now, putting the inversion symmetry operator there is psi s minus r minus capital R. Now I know that this is an even function, so I can change the sign of the argument. So this is equal to psi s of r plus capital R. And this, if we now go back to a creation operator, is equivalent to creating the particle at the point minus capital R in an s orbital. We changed minus r to plus r, so it's the capital R that is changing sign. So if I have a lattice and I do an inversion around the origin, my local orbital is centered around side r. After inversion, it's centered around side minus r. So that makes a lot of sense. And the S wave function is even, so otherwise nothing happens. So with this small intermezzo, we can go back to our original state, and our original state then is square root 1 over v, sum over all lattice sides, e to the I, k dot r, a dagger minus rs, acting on the vacuum. Now as we sum over all lattice sides, we can also sum over minus all lattice sides, so I can change r to minus r everywhere. And that is the normalization, square root of r, e to the minus I k r, a dagger rs out of the vacuum. And this is equal to a dagger minus k s acting on the vacuum. So inverting a Bloch state with wave vector k out of an s, built out of s local Wannier orbitals, gives me the Bloch state with a dagger minus ks. The same we can do, but now not for the s orbital, but for the p orbital. And we then find that we can go completely through the same argumentation, but instead of having here an even function, it's an odd function. So we get an additional minus sign. So a p Bloch state is going to minus the p Bloch state at minus k when you do an inversion, and the s Bloch wave is going to the s Bloch wave at minus k with a plus sign. So we see that these states are not just even and odd. For an even and an odd state, this should have been the same, but we get, of course, a plus or a minus sign, but also a change in the state that we have. For symmetries and point groups, that's perfectly fine. This is not a one-dimensional irreducible representation, but a multi-dimensional irreducible representation. And then you're allowed to just change the state with which you are degenerate. So we can still say that this is an even and that is an odd state, because we just look at how it behaves under inversion symmetry, but you don't return to the same state in them. Good, let's make a single degenerate state out of it that under inversion symmetry goes back to itself. And for that we can look at the state where we create a particle at minus k and we create a particle at k out of the vacuum. If you do an inversion symmetry on that, then the state at k goes to minus k and the state at minus k to k. So this becomes a dagger ks, a dagger minus ks out of the vacuum. We now can commute our creation operators and that gives you a minus sign. A dagger minus ks, a dagger ks out of the vacuum. So a wave function made out of two Bloch waves, one at k, one at minus k, of Wannier functions that are even, is odd. Because I, under inversion symmetry, change the order of my creation operators and therefore change the sign of that wave function. We can do the same, but now for the p orbital. And also here we find that the state at k is going to the state at minus k and the state at minus k is going to the state at k. Now this state picks up a minus sign and this transformation picks up a minus sign. That is two minus signs, such that we in the end have one minus sign because of the commutator and two more minus signs which cancel each other because your local Wannier functions are odd. And we find that a Bloch wave or a Bloch state with the creation of two states at k and minus k for a Bloch wave function that is made out of locally odd Wannier functions is odd, just like creating them out of S states. Now we have to be a bit careful. We can do this except for a few exceptions. For the case where k is equal to 0, or the case where k is pi over a, we have that k is equal to minus k. Right, this is not the momentum, this is crystal momentum, such that your crystal momentum is periodic with a range such that k equals 0 is equal to minus 0 and pi over a is equal to minus pi over a. So for those wave vectors you're not allowed to build states like this. And we will have to treat these points separately. These are known as the time reversal invariant momenta, or trim points. And as we will show later, it is the trim points that in the end determine if your state is even or odd. Now, saying when I have two electrons in my band, I have an odd state is not nice, because then you can have 4, 8, 6, and you will always then have a question, am I even or odd? So we can now make an even state where we create the state at k, we create the state at minus k, we create the state at pi over a minus k, and we create a state at k minus pi over a out of the vacuum. And this is even, independent if our orbital is even or odd, that we use to create those states. So with that we can generalize that our state where I make a product of my complete band and my orbital is some linear combination of an S and a pz orbital, which you have when sp sigma is no longer 0, is even for all electrons that don't sit at time reversal invariant points, because you can always find 4 of those, and 2 of those can either be even or odd, but will just give you a sign change because of the commutator, and 4 of them you'll have 2 times the sign change such that nothing changes again. So that if we now look at our inversion of that state, this is equal to, well, we have to look at the time reversal invariant points. So we look at the point where k is 0 and see if our Bloch wave is even or odd. We look at the case where k is pi over a and see if your state is even or odd, and I have to create here and then for all other states you're just coming back to yourself. So we do not have to look at all states, but we can focus on just 2 Bloch waves that make, or we don't have to look at all one-particle states, but we only have to look at the parity of 2 of the Bloch waves. Now, at k is 0 or pi over a, we have that sign chi a is 0, such that there is no mixing, which means that tau k, for the case where this is 0 or pi over a, is an element of either S and pz. Now if we look at the parity of our S state, then we have here an s orbital and there an s orbital. So we have +1 times +1 times phi, and this is even. If we look at our pz orbital, then we have -1 times the wave function, so also this is even. So if you look here at your bands, then you see that for the case where we have no mixing, you always have even bands. For the case where they overlap and sp sigma is non-zero, you see that you have a gap opening. Now in this case we can have a difference between an even and an odd state at k is 0 and k is pi. So if we find at gamma an s orbital and at x a pz orbital occupied, then our state is odd. And the same is true if you find at gamma a pz and at x the s orbital occupied. Also in that case, your state is odd. So you are able to make odd wave functions only if your S and P band overlap and an hybridization gap occurs, then such that at gamma and at x either the S or the PS orbital is occupied, so you have 2 different orbitals occupied at these 2 momenta, then your total many electron wave function is odd. So if you would be able, for example, to change as a function of pressure the bandwidth of the S and the P orbital, and you start out for a case where they are close to each other and nearly touching, then when you increase your pressure, your bandwidth increases, and a gap or a mixing would happen, and hybridization gap opens, and you have a phase transition between an even and an odd state. I'm not aware of materials where you can really do this other than in theory. There are materials where you have an odd ground state wave function, and there are materials where you have an even ground state wave function. And what we will show later is then at an interface between states where you have odd and even ground state wave functions. Also there, strange things happen at the surface between those interfaces. But for that I want to discuss topology first, and basically not describe this as a transition between different irreducible representation states, but as a transition between two states that have different topology. For now, thank you very much. I hope to have shown you a nice example where you can use also some unconventional characteristics of your system as the order parameter. For example, the irreducible representation of your wave function, and how even in a tight binding model we can make such kind of phases and phase transitions. Stay healthy. We see each other later.